Okay, so the recording is started. Can you already see the screen, the slide?
Yes, teacher.
Okay. So today we will consider the very first application of MOSFET, that is for analog amplifier. Can you already hear the sound?
Yes.
Okay, perfect. Okay. So again, in the last chapter, we have considered the basic about field effect transistor, including the structure, the working principle, the basic characteristic curve, including the output characteristic curve and the transfer characteristic curve, right? So for field effect transistor, we don't have an input characteristic curve because at the input we have only the voltage between the gate and the source VCS, and the current at the gate IG is nearly equal to 0. So for BJT we have three important characteristic curve. That means at output, the most important one is the output characteristic curve. At the input, you have the input characteristic curve, and the relationship between the input voltage VBE and the output current IC, you have a transfer characteristic curve, right? For field effect transistor, because the input current IG is equal to 0, we have only two important characteristic curve. So the output one, the relationship between the output current ID and the voltage output voltage VDS, and the transfer characteristic curve. So the relationship between the output current ID and the input voltage VGS. Okay. So again, these two characteristic curve is very important, right? So you have here, for example, we consider the n-type, n-channel MOSFETs, for example. So the drain is here, the source is here. The arrow here indicates that the current running from the drain to the source. That means the charge carrier are moving from the source. For the n-channel, the charge carrier is negative, so electron, so negative charge is removed from the source to the drain. Okay, so that means because electron is the negative charge, if electron is moving from the source to drain, then the current is moving in the opposite direction, so from the drain to the source. Okay, so and you have the gate here. Okay, so at the input you have the terminal parameter is the current IG here, which is approximately equal to 0 because you have an oxide layer here. Okay, so we are considering the mode. So between the gates and the channel, you have an oxide layer here, which is a good insulator. Okay, so it can be silicon dioxide, SiO2. It can be high K material, for example, gallium nitride, boron nitride, etc., or silicon carbide, for example. Okay. So, and as you have the voltage, input voltage applied between the gate and the source, so VGS. So at the input, because the current input current IG is equal to 0, we don't have an input characteristic curve, right? At the output, you have the current output current ID here equal to IS, okay? Because the current IG is equal to 0, then ID and IS is equal, and you have the voltage drop between the drain and the source. You have a VDS here. Then you have the output characteristic curve, right? So VDS here and ID here, right? So when VGS is less than threshold voltage, then it cannot create the channel here. Okay, so the channel here is not created, so there's nothing to connect between the drain and the source. So whatever the voltage that you put between the drain and the source, because there's no channel, that means no carrier, there will be no current. So ID is equal to 0, and the transistor is in the cut-off mode. Okay. So when you increase VGS, the input voltage, so that is become higher than the threshold voltage. Okay, so then you can attract electron minority charge from the body to create the channel here that connect the drain and the source. And if you apply a positive voltage between the drain and the source, then you can create an electrical current. Okay, so if you apply a VDS positive, then an electrical field between the drain and the source will accelerate electron from the source to the drain. That means you create a current running from the drain to the source, right? So the higher the VGS, so here is VGS larger than threshold voltage. Okay, the higher the VGS, you can attract more electron in the channel, right? So that means with the same voltage VDS, you have a bigger current of ID, right? So increasing more increase VGS, you can increase further the current ID. Okay, so this VGS in the increasing direction, right? So, and in the if VGS is larger than threshold voltage, then you have two different working region of field effect transistor. Okay, so limited by the boundary here. Okay, there's some boundary here. The boundary here is on the left side. When VDS is still small, so VDS less than VOV. So VOV, the overdrive voltage is the difference between VGS and the threshold voltage, right? So overdrive, that means how higher VGS compared to the threshold voltage VTM. Okay, so don't forget that for most of any time field effect transistor, the threshold voltage here is somewhere between 1 volt and 3 volt. Okay. So on the left side, the transistor is in the triode mode when it's behavior as a resistor. Okay, with the slope of the resistor is the slope of this curve. Okay, this part of the characteristic curve can be approximated at a straight line. Okay, and of course, the higher the VGS, the steeper the slope here. That means the lower the resistor, right? So because the higher the VGS, more electron you can attract from the substrate to create the channel, and there are more electrons in the channel. That means the channel can conduct electrical current better. That means the resistance is lower, right? So the resistor we already on is inversely proportional to VGS. So the higher the VGS, the lower the resistor, right? And on the left side, when VDS is large enough, VDS larger than the threshold voltage, it can create the pinch off of the the pinch off of the channel, and that means the channel reach its saturation state. That means when you increase further VDS, it will not enter the channel, and the current ID is constant, and it does not depend on VDS. It just depend on VGS. And of course, the higher the VGS here, more electron, more carrier we attract to the channel, and we have a more current. Okay. So is go similarly for the p channel field effect transistor. Okay, so on way the gate here for p channel the carrier here is positive, so hole is start from the source, okay, and run to the drain. Okay, so if the positive carrier run from the source to the drain, that means the current also, okay, the current run from the source to the drain. So the arrow is in the opposite direction. It indicates that the current run from the source to the drain. And in order to attract the positive carrier from the body to the channel here, you should apply a voltage VGS here, negative, right? Okay, voltage VGS negative. So the only difference between the P time and N time, you just reverse the direction of the current and reverse the polarization of the voltage. Okay, and of course, in order to accelerate the hole from the source to drain, you should apply a positive voltage at the source and a negative voltage at the drain. So VDS here must be negative, okay, to create an electrical field from the source to the drain to accelerate the positive charge from the source to the drain. Okay, so that is the very basic thing. Okay, so as with BJT, you can see that when the transistor is in the cut-off mode, you can replace the transistor by an open circuit. Okay, so between the drain and the source, there is no connection. So the current ID is equal to 0. The transistor can be used at an open switch, a closed turn-off switch, right? In the triode mode, okay, the transistor, the voltage drop between the drain and the source is small here, okay. So the diodes can be used at a closed switch, but the RD between the drain and the source is quite large here. In this case, we cannot omit the RD here. We count as RDS on. Okay, so the transistor can behave as a switch that is turned on, but it's not an ideal switch because there is a resistance between the two contacts of the switch. Okay, so in the saturation mode here, you can see that the output current ID is proportional to only in the ideal case is proportional to only the input voltage VGS. Okay, so this is the relationship between the output current ID and the input voltage VGS is reflected by the transfer characteristic curve. Why? Okay, to characterize how an input parameter VGS can control an output parameter ID. Okay, so you can see here the characteristic curve. If the threshold voltage VTN is here, then you can see that when VGS is lower than the threshold voltage, then we cannot create the channel here. We cannot create the channel here, right? So there is no channel to connect between the drain and the source. That means the current ID is equal to 0. Okay, and when the threshold voltage is larger than when VGS input voltage VGS is larger than threshold voltage, you can create the channel here, and then we have a current ID here. Okay, in the triode and saturation mode, and in the especially in the saturation mode here, you can have the simple relationship between VGS and ID. So you can have ID equal to Kn over 2 VGS minus V threshold square. Okay, so this curve is a parabol. Okay, parabolic curve. Parabolic curve. Okay, relationship. And if we have the output parameter ID proportional to the input voltage VGS, okay, so we can think about building an amplifier, okay, using transistor, few effect transistor bias in the saturation region here, okay. We just use a small variation of the input parameter VGS. So it can be VGS can be from the signal source, it can be from a sensor, from an antenna, etc. So the signal source, okay. Whenever it's signal source, you can modelize the signal source by a Thevenin equivalent here. So here the voltage of the signal source, and here the internal resistance of the signal source. So this variation, if you put at the input between the gate and the source, then just a small variation of the input voltage here. Okay, so as you can see here, when VGS1 here, you have ID1, and just small variation of VGS2 here, you can have a ID2. So you have a delta I D here and delta VGS here. Just a small variation of input voltage delta VGS can induce a bigger variation of the output current ID. Okay, and the relationship between to characterize this change, we use the transconductance Gm is equal proportional to the delta I D over delta VGS. Okay, so that's what we have studied from the last chapter 7 about the basic characteristic curve of the field shape transistor. Okay, so today we will focus on the very first application of a field effect transistor. Okay, in the saturation region here. Okay, so in the saturation region here, when ID is proportional to VGS, or we consider this part of the input characteristic curve or this part of the output characteristic curve. So we can use the field effect transistor once is biased in the saturation region to build amplifier. Okay, and you can see that it's very similar to the amplifier using BJT. Okay, so you have a 3-terminal gate, drain, and source. Okay, the 3-terminal gate, drain, and source of field effect transistor is very similar to the 3-terminal base, collector, and emitter of bipolar junction transistor. Okay.
Question, please.
Yes.
In the ED VDS characteristic EV curve, why
the transfer characteristic curve?
Yes. Why we do not have the negative part, just the positive part?
Negative part?
Yes,
you
like
mean,
just like.
You
no,
mean negative? You mean negative value of VGS?
No, the other VDS and ED, the above, the left one. Yes.
This one, the transfer characteristic curve. Here?
Yes, yes. Why we do not have a negative part like BGT?
So you are asking about the the end time, right? So we the end time, and for P time you just reverse. So for the end time, the channel here, in order to create the channel here, you should apply a VGS, okay, positive to create the channel. And when the channel here, the channel is formed with electron, so negative charge, okay. So that means I will try, okay, I will erase on here. And we will try to see at the negative part, what happened in the negative part here. Okay, so you have a output characteristic curve VDS, right? And ID here, right? So we just considering the positive part here, right? So that means when VGS. So how about the negative part here of the characteristic curve? So you mean there may be some negative part here, right?
Yes, yes.
Okay. So for field effect transistor, because the channel, okay, so we can draw. So the gate here, the drain here, and the source here. So we are considering the end time, right? So the end time, the body here is the P time, okay? So that means the majority charge carrier is whole, and the minority charge carrier here is electron. Okay, so when you apply a positive VGS here, so for all of this is VGS larger than threshold. Okay, so that means you can attract already electron to form the channel. Okay, so you have an electron here, negative charge here to form the channel. Okay, so if in this part of the characteristic curve, okay, so that means when you apply in this part, that means VDS is negative, right? VDS is negative, right? So that means VDS is negative. So I will use another color. So if VDS is negative, so negative here and positive here, then the electrical field will have the direction from the positive to negative, right? Right? Are you following?
Yes, yes.
Okay. So if the electrical field is from the source to the drain, okay, so it will accelerate the electron, so negative charge, to move from the drain to the source, right? So the electron is negative charge, so it will move in the opposite direction with the electric field. Okay, so you can create a negative current here. Okay, so in the opposite direction. Okay, so but we don't care too much about this this negative reason here, because this current is quite small. Okay. Okay. Of course, whenever there is charge carrier, if we apply an electrical field, we can create a directional flow of charge carrier, and then we can create a current. Okay, so in this case, we reverse the current ID. Okay.
Okay.
More question? Okay. So if not, we continue to consider the amplifier using field effect transistor. So because the field, as with BJT, field effect transistor have a 3 terminal. Okay, so the gate here, the drain here, and the source here. So if we are considering the end time, for example, so we have a 3 configuration. Okay, so if the input signal is fed to the gate and taken from the drain, then we have a common source. Okay, and it is the inverting amplifier. It's very similar to the common emitter of field effect of BJT. Okay, so BJT is here. Emitter, collector, and base. Okay, so for for BJT, we have a study if the input signal is fed to the base and the output signal is taken from the collector, then we have a common emitter. Here it's very similar. If the input signal is fed to the gate and the output signal is taken from the drain, then we have a common source. Okay, so it's inverting amplifier. So if the input signal is fed to the gate and the output signal is taken from the source, then we have a common drain or the follower. Okay, common drain. And if the input signal is fed to the source, okay, and taken from the drain, then we have a common gate. Okay, non-inverting amplifier. So common gate is very similar to common base. Common drain is similar to common collector, and inverting amplifier is common source is very similar to common emitter. Okay, so we follow the same procedure for analysis. The step 1 is DC analysis. Step 2 is AC analysis, and replace transistor in this time the few effect transistor by its small signal model. Okay, then we replace the input signal by its Thevenin equivalent, replace the load by a Thevenin equivalent, and we will draw the AC equivalent circuit, and we will calculate the output voltage, the output current in order to deduce the voltage gain, the current gain, the power gain, etc. We will calculate the coupling and bypass capacitor also, okay, to ensure that at the AC mode, the coupling and the bypass capacitor can be considered a short circuit to conduct AC signal. Okay, so and of course we will use the LT spice to verify our hand calculation. Okay. So we will go very quick because it shows very similar to that of amplifier with BJT that we have studied. Okay, so the only difference it just how to calculate the biasing point, Q point. Okay, we have studied that from the previous chapter. Okay, so there's small signal model of few effect transistor is a little bit different compared to the BJT. So this is the only difference. If not, the procedure, the AC circuit for the DC circuit replace capacitor by open circuit, and AC circuit in AC mode replace capacitor by short circuit, etc. And draw the AC equivalent, replace transistor by its small signal model, etc. The whole procedure is always the same. Okay. Okay. So again, in order to use the few effect transistor at amplifier, okay, we have to bias the transistor in the saturation mode. Okay, so in this part of the characteristic curve. So two conditions in saturation region. Okay, the first condition is of course VGS higher than the threshold voltage VTN or VT or sometimes VT. Okay, so it's larger than the threshold voltage by an amount of overdrive voltage VOV. Okay, so you can see here that means VOV is equal to VGS minus V threshold. Okay, so V overdrive voltage reflect how big VGS compared to the threshold voltage. Okay. And the second condition is that in order to put the transistor in the saturation region, the VDS must be large enough and larger than overdrive voltage. So two conditions to put the transistor in the saturation mode. Okay. And we know that in the saturation mode here we have the output current ID proportional to the input voltage VGS only by the simple equation. So ID equal to Kn over 2 VGS minus V threshold square. Okay. Okay, so by this simple equation. Okay. Again, compare with the BJT, you can see that for BJT in the forward active region, the output current IC is proportional to the in the forward active region, the output current IC is proportional to the exponential of the input voltage VBE. Okay, so that means it's increased very fast compared to VBE, and we know this increasing. So 60 millivolt per decade. Okay, we have considered that quantitatively in the previous chapter. Okay, for BJT, just a small delta V of the input voltage VBE, only 60 millivolt, can induce a change of 10 times delta IC 10 times. Okay. For few effect transistor, this amplification effect is less important because the relationship between ID and VGS is not an exponential; it's just a quadratic relationship here. Okay. Okay. So, and in order to put the transistor in the saturation mode, you have to use a biasing circuit. Here is the 4-resistor biasing circuit. Okay, in order to have a VGS, to create a VGS larger than threshold voltage here, and a VGS here larger than overdriver voltage. Okay, so that is the. So we have a three configuration that we have just talked about that. So the common source, common drain, and common gate. Okay. So we will now consider the very first configuration. So common source. Okay. So you can see here on the left side is the bipolar junction transistor. So BJT, so 3 terminal, the base, the collector, and the emitter here. And on the right side, so you have here field effect transistor, MOSFET. Okay, with the 3 terminal gate here, drain here, and source here. Okay, so base here, collector here, emitter here. So the common emitter, that means the input signal is fed to the base, and the output signal is taken from the collector to supply to the load. Then you have the emitter is in common. Okay, so you have a common emitter for BJT. Similarly, for field effect transistor, the input signal here is fed to the gate, and the output signal is taken from the drain to supply to the load. So the source terminal is in common. So we call that common source. Okay. The AC equivalent circuit is totally the same. Okay. The only difference is the small signal model of BJT and the small signal model of field effect transistor is a little bit different, just a little bit different. You will see later. Okay. For BJT, you have the common collector. So common collector, that means the input signal is fed to the base, and the output signal is taken from the emitter to supply to the load. That means the collector is in common. You have a common collector. For the field effect transistor, you have the similar configuration when the input signal is fed to the gate and the output signal is taken from the source to supply to the load. Then the drain here is in common. So you have a common drain circuit. Okay. Again, the AC circuit is totally similar. Okay. So you can see here the AC equivalent circuit is totally similar. Totally the same. The only difference is the transistor here. Here you have a BJT. Here you have a few effect transistor. So the small signal model is a little bit different. Okay. And the last one is the common base. Okay, for BJT, for the common base, the input signal here is fed to the emitter, and the output signal here is taken from the collector to supply to the load here. That means the base here is in common. So you have a common base. Okay. Similarly, for few effect transistor, the input signal, okay, here is fed to the source, and the output signal here is taken from the drain, okay, to supply to the load. That means the gate here is in common. So you have a common gate configuration, okay. So as you can see here, the AC equivalent circuit is always the same. So you can see here this part, including the signal Thevenin equivalent of the signal source here and RS6 here. Here is very similar, okay. So at the output you have RL, you have RL here, okay. And the only difference is the transistor. Here is the BJT, here is the few effect transistor. So we should replace this transistor by its small signal model, okay. For the AC circuit is nearly totally similar, okay. Okay, so let's take a short break of 10 minutes before we come back to consider the very first configuration, the common source amplifier using a few effect transistor here. Okay, so short break. We will come back at about 3:20 p.m. Okay, 3:20 p.m.